Let me share my screen. Okay, so I've been working on the problems. I am done with all of section A, the wiki problems, all of section A, and I have about half of the section B problems. Yeah, I think there are 6 wikis, and I have 3 completely done and part of the others. So I'm actually more than halfway, maybe like 70%, 80%, 70% done. So you can take a look to practice. I've decided to move the exam, postpone it by a week. So not on March 2nd. March 2nd was the original date, right? Which is a week from today. Let me just double check my dates. I don't want to make a mistake here. So yeah, a week from today was the original date for the exam. We'll move it to March 9. So exam 1 moved to Tuesday, March 9. So 1 week after the original date. So that will give us more time to finish with CND. Now, I'm going to change the due date for the CND problems. I set it on Thursday. But here's the thing. I set it on Thursday because, as you can see, I usually can work on the problems. I don't know, for those who had already well, everybody had problems due, so I usually work on them Thursday evening, Friday all day. And so if you want comments, and you still want some time to work on it and still get full credit, then try to upload by Thursday night, or even more, Friday morning, before I start working on the problems. But I will move. So I will still take problems until Saturday. So for wiki problems, um, from sections C and D, let's say that you have 2 due dates. If you want comments, keep the Thursday due date. Thursday, if you want comments, anytime on Thursday. And if you do it overnight, before I go in and check them on Friday morning, that's still okay. But think about Thursday as your due date. But you can upload all the way to Saturday. So I just say Saturday for all. So you upload by Thursday or Friday morning. I'll go over them all Friday. I give you some comments. You still have time to go over your problem Friday and Saturday, or let's say Saturday, because I don't know what time of the day I will go over yours, but you might have some part of Friday. And then, on Saturday, I'll close it so that I can focus on having that ready, hopefully by the beginning of the week. Kind of what's happening now with Section B. But then that will give me time to finish everything and you time to practice for the exam until the 9th. That makes sense?
Yes. So by Saturday,
so
do you mean
those
this
are
Saturday?
This Saturday. What day is that? The 27th. So the original date was 225. So now I'm actually moving it to 227. 227. So
that's a lot of problems to deal with.
but you only have to take care of your own, right? And then you'll still have one more.
I've been trying to do all of them only
yes,
because
you should.
Because for some,
you should.
yes, for some though, there's a little bit difficult, and then some I can maybe do, but it all takes a lot of time for me to think about. And
Yeah. So remember, all these problems are assigned to all of you. So you should try all of them. But the idea is that you can check your answers, you can compare your answers to whatever is in the wikis at the end. You're responsible for one or two problems on the
right,
wiki.
which is what I do first priority.
Yeah.
But then I worried about trying to do all the others because some of the wiki problems are missing, and it already reached its due date.
Yeah,
Like,
but think about it, you know, think about it as the due date to know, or to have checked all the problems on your own, and compare them if you need to the wikis and all that. You can think about that being the day of the exam, or what is this, March 6th, which is a week after. So the idea is that the problems won't be all ready by the 27th. I mean, you all should upload your own problem by the 27th. You know that's okay, that's realistic. You still have the rest of the week. But then from the 27th to the 6th, I need to make sure that all the problems are ready for you, right? The earlier the better, so that you can access to correct solutions. But so
okay,
really, the deadline, let's say, for you to go over all the problems, you can think it's the 6th, a Saturday after, or even the 9th, which is the exam.
okay. I was like,
Yeah.
because I saw some missing, I thought I have to try and figure it out on my own. But then I was worried about sacrificing too much time to deal with the homework, the wiki problems instead of my other classes. So this helps a little.
Yeah, you'll have all the problems. Again, the idea is that everybody will have access to correct solutions, by the 6th. But you should keep track. If you try to do everything on the 6th, that's going to be too late. You should keep trying all the problems and checking the solutions as we go. All right?
Yeah.
Okay. Any questions about this? Okay. So last time we talked about distributions of partitions, and I had, let me see, I had this table for a very specific problem, right? Well, set of problems, because here we had 10 balls into 3 boxes, and you could have all these possibilities. So we had a total of 8, let's say, standard problems, which were depending on whether the balls were different or equal, same for the boxes, and also whether you allow empty boxes or not. Mhm. So I'm gonna try to generalize this table for an arbitrary number of balls and boxes. So M balls and N boxes. So I just kind of copy this frame on a different page with empty cells in the middle, so that we can fill them in for general numbers of balls and boxes. So that's what I have over here. Mhm. So as you can see now, I have the difference is that now I have M different balls, N different boxes, and that way we can review what we did last time, and then we can work with that in a specific problem. So also for today, I have the next class activity. If you don't have it yet, if you want to print it or something, we'll use it in a few minutes. All right? So let's see. Just to remind you, again, the easier parts, the easier cells for this table are, let's say, the first one, this one, and the key question is where the balls go. So, each ball can go into any of the boxes. So you can think about this problem as a strings problem. So, you have your spaces here that are labeled by the balls, and each one has n possibilities. So this is either box 1 or box 2 or box n. And so this is n times n times n all for all of them. So this is just n to the n. Mhm. So that's what we have there. Okay. For this one over here, in general, for all the balls are different. You still have m of them. So m identical balls into n different boxes. So now what you do is, how many balls in each ball. So this is equivalent to solving the equation x1 plus x2 all the way to xn, n boxes equals m. And all of the xi's are greater than or equal to 0. There can be empty boxes. Mm-hmm. And so the answer to this one is just the, n plus m minus 1. So, or maybe let me put it in the same order as usual. So we have m1's n minus 1 separators, and we can choose either one, m or n minus 1. Mm-hmm. And then we jump into that one, where the only difference is that we don't allow empty boxes anymore. So what that means is that we have the same equation, but this time the x's are greater than or equal to 1, right? So this time around, we first place one ball in each box. So now we have m minus n balls that still can go anywhere. And then we still have n minus 1 separators. And then we're choosing m minus n. Maybe, okay. Okay, so this will be it. I think, it's better to remember this one instead of its simplification. Its simplification is just n minus 1, choose n minus n, or you could even do n minus 1 here. Those two things are the same. Maybe I'll do it in 2 steps. n minus n, or this is the same as n minus 1, n minus 1. But I think it's better, even though it's not simplifying, I think it's better to remember this one. If you understand that we have n minus 1 separators, and then we have m ones, but since we can first distribute one ball per box, we actually have n minus n balls to be distributed with no conditions, so that it looks more like this one. So I think it's better to remember this one, but whichever you prefer. Okay, so for the others, we need those definitions of T numbers. This is the definition of a T number. So this is going to be the T number Mn. Mm-hmm. And then we'll talk about how to compute that. That's the T number Mn. This one over here. So that's different balls into different boxes. And this is the one we talked about the most last time. And I'll get back to it. But for now, I'm just going to write the definitions the definitions of the special numbers that we need. So that's going to be T numbers, different balls into different boxes. Identical balls into identical boxes are the partition numbers. So in how many ways we can write a number into a given number of parts. I'll write that in a second. And then the Stirling number. So different balls into identical boxes. This is called the Stirling number, SMN. So those are definitions. This is the same way that we define, combinations of n objects, choosing k of them, k different ones of them is the binomial n choose k. When we've been using that as a definition. Same thing with these numbers. So TMN is just the number of ways of distributing n different objects into n different boxes. Mm-hmm. So let me write that on the side, here on the side. Mm-hmm. So here. So TMN is by definition the number of ways to distribute m different objects into n different boxes no empty boxes allowed. And then let's do, I think let's do SMN first, because these are more related to each other than with the permutation, with the numerical partitions. So SMN is almost the same thing, but now the boxes are identical. So number of ways to distribute different objects into n identical boxes. No empty boxes allowed. And so the difference you can see is different goes to identical there. Mm-hmm. And then PMN, those are the numerical partitions. This is the number of ways m, the number m can be written as a sum of exactly n positive integers. Order is irrelevant. So it doesn't matter the order. But as we had it last time, 10 equals 1 plus 1 plus 8 is considered the same partition as 8 plus 1 plus 1. The order is not important. Okay, so those are the definitions. Now, given the definitions, we also have formulas. Not for the partitions, not for the numerical partitions. We're going to learn more about them. But we do have a formula for the TMN, and we have a formula for the the Stirling number in terms of the T numbers. So the Stirling number is just the T number over n factorial. So if you know how to compute the T number, then you're fine. Mm-hmm. Now, to compute the T number, we talk about two ways of writing it. But the one that is more easily used is this one. So TMN, I'm going to write it as a dot product. So I imagine that all of you have seen dot products maybe in linear algebra, but it's just notation. So I'll remind you. So TMN is just the dot product of the the nth row of the Pascal's triangle. So this is supposed to be n choose 0, n choose 1, n choose 2, all the way to n choose n. Times, so this is going to be the dot product of n to the m and minus 1 to the m. So these are powers of the mth power of an integer. Oops, maybe I should move this a little bit more to the right. Yeah. And so here you just keep decreasing the base, right? So n minus 2 to the m, and you keep going until you get to 1. Oh, I need to, give me 1 second. I need to alternate signs. So let me start over from here. So the first one is positive, but then the next one is negative, and then the next one is positive, and you just keep alternating signs. I'm just gonna move this over here. So you just keep alternating signs. So I'm gonna write one more. And so until you get to 1 to the m. So you're gonna have negative 1 to the n minus 1, 2 to the n, negative 1 to the n, 1 to the n. Just like that. So this is the nth row of Pascal's triangle. And these are the mth powers, alternating signs. Okay, so let me show you how this works. For, let's say, last time we had T103, right? So I'll show you here as an example how this works. So T103 is, you do the binomials. So 3 choose 0, 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. Dot product, I'm gonna write it below the other one. It's the same number of entries. So the powers of 3, I mean the 10th powers of 3, 2, 1, 0. So 3, 2, wait. I'm missing, give me 1 second, I'm missing one term here. Okay, I'll correct my formula in a second. Let me write this. And then I alternate signs. So that's a minus, positive, minus, and so on. So let me just, yeah, let me do this. This is supposed to be, so it's n minus 1 terms. So this one is supposed to be 1, and this is supposed to be 0. So that dot product just becomes, you just multiply first entry times first entry plus second entry times second entry, and so on. So this just becomes 3 to the 10, 3 choose 0, minus 2 to the 10, 3 choose 1, plus 1 to the 10, 3 choose 2, minus 0 to the 10, 3 choose 3. So just multiply vertically and add them up. That's the dot product. You're just multiplying the kth entry times the kth entry, and then add them up. Add them all up. Yeah. So this is 3 to the 10 times 1. 3 choose 0 is 1. 2 to the 10 times 3. 1 to the 10 times 3. And 0 to the 10 times 1. So you see, these are the entries of the Pascal's triangle, right? The 1, 1, 1, 3, 3, 1. Right? So those are the coefficients. And then I multiply it times the powers, the 10th powers of 3, 2, 1, 0, and I alternate signs. So this is 3 to the 10th minus 2 to the 10 times 3 plus 3. And you can just get that number. I had it before, so I'm just gonna copy that. Make sense? So this is one way that you can compute it. And we're gonna see how after the exam, when we see inclusion exclusion, we're gonna prove that formula for the T numbers. Okay? But you can use it. And so there are a couple of problems in the wiki assignments that I said, please compute or reduce your answers to a whole number. So, it's just for whoever got those problems to practice doing something like this. Instead of just writing your solution as T103, actually figure out what that number is. Questions? Okay. So once you have that, if you need the S103, you can just take that number over here.
Does that say Stirling numbers of the second kind?
Yes.
What's Stirling, though?
It's a name. It's a last name.
Oh.
Yeah, whoever came up with them and used them for something important. I can tell you more about it later. But yeah. So maybe I should write here, this is just the previous value divided by 3 factorial. So this is just that 55,980 divided by 6. And that happens to be that. Okay? So these were the values that we had last time. But that's where they come from. We computed, by the way, and you can review it, we computed T103 in a much longer way. And that's important because for some examples, you actually need pieces of it. And this formula is kind of already a very nice reduction. So it's difficult to abstract, it's difficult to extract some of the pieces, partial pieces that you might need in other exercises. So, when we go through the class activity, you'll see what I mean. But this is the easiest way to compute a T number. So once you have those, look, I'm still missing the numerical partitions, right? But once you have those, you can compute these other these two cells over here. So I'm gonna move over there. I'll upload everything later so that you have it in case you're missing something. So once I have those two, once I can compute those two, I can compute, I can use, or once I define those, I can actually figure out what goes in here. Because you see, this is not allowing empty boxes. Here we allow empty boxes. So the only thing that we have to do is solve the problem when we use all the boxes, when we use only n minus one of the boxes, or n minus two of the boxes, or just, all the way just to one box. You can use any number of boxes, and each one of those is an Stirling number. So this one over here is just the sum from, let's say, k equals 1 to n of the Stirling number. Sorry guys, this is an m balls, and this is supposed to be n identical boxes. So the Stirling number m, so the number of balls is the same for all of them, but we can decide to use less boxes than n. So there's some that are empty, right? So when we use all of them, but none of them is empty, it will be SMN. If we allow one empty, it will be SM n minus one. Two empty, SM n minus two, and so on. So it's just that sum. Okay. So use, let's say k represents the number of boxes, the number of non-empty boxes. Mm-hmm. So you can have one non-empty box, two non-empty boxes, three non-empty boxes, and all of those are Stirling numbers. So we have the perfect notation to say what that is. Now computing that, it takes time, right? Because now if I want to solve my problem for 10.3, I have to find T10.3, T10.2, T10.1, and then divide those by factorials to become, Stirling numbers, and then add them all up. So, it's a lot of computations, but everything is doable because we have formulas for everything. Yeah. And then questions so far? Another observation is same thing that we did here, the same thing that we did here, that to go from the right column to the left column, we just add the Stirling numbers from k equals 1 to n. We can also do the same to go from the right column here, the t numbers, to the left column there. So if we did that, then we actually have a theorem / observation, which says that n to the m, whatever we got here, is the same as the sum of the t numbers from k equals 1 to, give me 1 second, I have to do a little bit more. Yeah, give me 1 second here. So I'm gonna use the okay, let me explain. So you see, this is the TMN is a number of ways to distribute m balls into n different boxes, right? So in the first column, I'm allowing to have empty boxes. So I can decide how many non-empty boxes I'm gonna have. That's the K, right? So how many non-empty boxes I'll have. And then, once I decided how many, I can choose those K empty boxes, that's n choose K. And then the number of ways to distribute the m balls into those boxes is T and K. Mm-hmm. So, this could be useful for some of the problems. Mm-hmm. So let me just explain here. K equals the number of non-empty boxes, and choose K selects the K non-empty boxes, and TMK is the number of ways to distribute the M different balls into the K selected boxes. And we can do that for any K. We can use 1 box, 2 boxes, 3 boxes, or any number of boxes. So maybe I should actually call this a theorem, because it's actually not a trivial result. It's really a combinatorial proof.
What do you mean by n to the m power, but then it's just a summation?
Yeah. So look, this is the n to the m. The n to the m here is the solution to the problem when you have m different balls and n different boxes, right? But you're allowing empty boxes. So this is the number of distributions.
Oh, okay.
This is the number of distributions of m different. Let me see if I can push this a little bit down. Oh, okay. Okay, so number of distributions of m different balls into n different boxes. Empty boxes are allowed. Okay, so on the one hand, the solution is n to the m, and we explain it here. On the other hand, you can do it using t numbers, as I was trying to explain here. Yeah. So they're equal, counting this same thing in 2 different ways. It's like in the pizza problem that we counted all the varieties of pizza in 2 ways. You know, checking which items you wanted. That was 2 to the n, and then the number of 0 topping pizzas, 1 topping pizza, 2 topping pizzas, and so on. It was a summation, so it's the same thing here. So we can do it in an easy, surprisingly easy way with using strings, and that will give you n to the n. Or we can say, okay, since TMN is by definition the number of ways of doing this using exactly a certain number of boxes, then I can separate it into other possibilities, whatever number of boxes or which boxes I'm using. And for each one of those, I use a T number to distribute. Okay. Questions so far? And so the only other thing that we're missing is the partitions. So we don't have formulas for the partitions. We do this by hand for small numbers. And we're talking more about partitions after the exam, a little bit before the exam too. But this, let me just add for now. This is a very hard problem. knowing partitions is a difficult problem. There's a recursive formula, but for now we compute this by hand, or meaning we just count them all for small values of m and n, like we did. I'll go back and show you. So here, you see, what I mean by hand is what we did, the kind of thing that we did last time. We just find all of the partitions, right? We started 118, 127. What if if the smallest number is 2? What if it's 3, and so on? So we just count it by hand. For now, we'll have a recursive formula very soon that you will be able to use to do it faster, but we don't have short form formulas like the one for the t numbers. Okay, and once we have that, same thing as we did for the s numbers, this one over here is just going to be a sum. We decide how many parts are going to be in the partition, and then we just add the partition numbers. All right. Okay, any questions? So I'll separate this into 2 pages, and I have everything for you on the Canvas site later today.
Professor?
Yeah.
It might be kind of related to the wiki problems, but is there a formula for, let's say, for n different balls, when the empty boxes are allowed, there are I'd say other n different boxes and maybe k identical boxes? Is there a formula for those kind of specific problems?
Yeah, let's do this. Let's look at the class activity, because that has variations of this, right? So these are like the standard ones. If you were told, for example, before we go into the class activity, if you were told that you had, for example, 5 blue boxes, 5 identical blue boxes, 10 identical red boxes, then you will use these. You could use the ideas or these numbers in some way. You first use it for the blue boxes, and then you use it for the red boxes, but you need to make sure like how the balls are going to, or maybe this one is easier. So if you had identical balls, you will need to somehow use these functions, but you need to, deciding on how you're going to use them, how you're going to combine them, that's a tricky part. Okay? So this is just the basis. Let's go to the class activity and see how we can adjust for some of those things, how we can combine these ideas in different problems, okay? And hopefully that will help. And we'll do more on Thursday as well. Okay.
Thank you.
So let me go to the class activity then. So here. So let's see how much of this we can do. Like which are more direct consequences of the table that I just have, or how we can combine things. Something that I didn't review, let me just very quickly, because you'll need it, is this. When we, maybe I should do that. So when we define the t numbers, I told you about the multinomial coefficients, right? And so the t numbers can actually be written as the sum of all the different ways, like this one, 10, 10, 3, is the sum of all these multinomials. These multinomials are just defined as, in this case, 10 factorial over a factorial times b factorial times c factorial. I have them in the next few pages here. So the binomials are defined over here. So I'll write that down before we start the class activity. But those are the number of ways of selecting, how many elements are going to go into the first box, how many are going to go into the second box, and how many are going to go, or which ones are going to go into the first box, the second box, the third box, but I need to have A in the first box, B in the second box, and C in the third box. Those are called partitions of type A, B, C. So maybe I'll add that to my other table. So these ones are called partitions of type ABC. Okay, and so we're gonna need that, but we'll see it in the class activity, and then maybe I'll have a summary for that after. I'll write it very clearly, maybe in the next page. But let's get started with this. So this says, find the number of ways to distribute 8 different balls. Oh, these were my boxes before. Anyways, 8 different balls into 4 boxes. So my balls are different. The boxes might vary. This one says the boxes are identical. 2 boxes have exactly 1 ball each, and 2 boxes have exactly 3 balls each. So here's the thing. So important things, you have identical boxes, you have different balls. So the only thing that I have to decide is how, well, actually, I was told how many balls go into each box. So let me maybe make a small picture here. So I have 4 identical boxes. I need to have 1 ball here, 1 ball in 2 boxes, and 3 balls in the other boxes. And because the boxes are identical, I just need to decide. Essentially, I'm just dividing my set of balls into four subsets. So that here I have 1, here I have 1, here I have 3, and here I have 3. But the order is not relevant or not anything like that. So these are combinations in a way, because the order is not relevant. So these are called partitions of type 1, 1, 3, 3. And so what we do is we choose, right? We're choosing from 10 balls that are available. We're choosing 1 for 1 box. One group has size 1, and then another 1, and then 3, and then 3. But that actually will tell me the first ball that I choose goes into the first box. The second ball I choose goes into the second box. But my boxes are identical. So because my boxes are identical, I need to divide by 2 factorial times 2 factorial. Because, if I place, for example, if I place ball 1 here, ball 2 here, and then let's say 3, 4, 5, 6, 7, 8. So this is what one possible arrangement, right? But these two boxes behave the same way. The boxes are identical. So having that is the same as having B2, B2, B1, B3, B4, B5, B6, B7, B8. So because those two count the same, I need to be divide by a 2 factorial. But this also, this also going to identical boxes, so I need to divide by another 2 factorial because this 10 choose 1, choose 1, choose 3, choose 3. It's actually assigning 1 to the first box, 1 to another box, 3 to another box, and 3 to another box. But the boxes that have the same number of balls can be rearranged in different orders, and therefore I need to divide by the permutations of those boxes. That's the 2 factorial for the 3s and the 2 factorial for the 1s. Okay, I think I'll give you more examples of this type later on. Let me just mark it with a star so that I remember that we need more examples like that. It doesn't fit into any of the 8 pieces of my, 8 cells in my table. It's almost part of the Stirling numbers, but we just have kind of the total, like the formula for all the full Stirling number, and this is only part of that. Okay, so I'll give you, if not today, next time I'll give you more examples like this. But let's look at the next one. So what you're doing here is just going to be, you're already given your distribution, how many in each box. So it would be this binomial, this multinomial, with that distribution 1, 1, 3, 3, and here you just divide by the multiplicities of the numbers on the bottom. So 2 factorial because there are 2 1s, and 2 factorial because there are 2 3s. Yeah.
Shouldn't the 10 be substituted by 8? Because
thank you. Yes, thank you. I don't know, I kept the 10 from my 10-3 example from before. Thank you. Yes, this is an 8. And so this one is just 1 over 2 factorial times 2 factorial times 8 factorial over 1 factorial, 1 factorial, 3 factorial, 3 factorial. Okay. Let's look at the next one. This one fits more into the table that we had before. So the boxes are identical and no boxes are empty. Boxes identical, no boxes are empty. Let me go back to my table. So here, the balls are different and the boxes are identical. So balls are different. This one right here, right? Balls are different. Boxes are identical. And I just realized that I'm missing an M here. So here, boxes are identical, no boxes are empty. So balls are different, boxes are identical, no empty boxes. So is this is the Stirling number, whatever number of balls we have, that's 8, right? And whatever number of boxes we have. So S, so this one is S, 8, 4 boxes, right? So it's 4 boxes, 4. S8, 4. And if you wanted to compute this, that's T84 divided by 4 factorial. And this is just, remember, the dot product of the fourth row of Pascal's triangle, the 1, 4, 6, 4, 1. So this is 4, choose 0, 4, choose 1, 4, choose 2, 4, choose 3, 4, choose 4. So that's the fourth row of Pascal's triangle times the powers of the 8 powers of 4, 3, 2, 1, 0, and alternate signs divided by 4 factorial. So if you wanted to actually compute the number, you could do that. And just remember, this is the dot product, which means that you multiply 1 times 4 to the 8, 4 times negative 3 to the 8, 6 times 2 to the 8, and just add them all up. Multiply corresponding entries and add up. Now, this one is a good example of how, it doesn't directly apply, the table doesn't directly apply, but different parts of it do. So the boxes are identical, and at most one box is empty. So boxes are identical, different balls, identical boxes, it means Stirling numbers. Right, so different balls, identical boxes is the last row in your table. Those are Stirling numbers. Now, the question is, the right column is no empty boxes, but here we actually allow at most one empty box. The left actually allows any number of empty boxes. So it doesn't perfectly fit in either one of the two cells. So let me go back. So I'm talking about this, right? So different balls, identical boxes. But this is no empty boxes. Yeah? Comments, questions?
So would you,
Yes, so,
I'm sorry, would
okay.
you in that left column then and just represent the K as at most one empty box?
Exactly.
So if we have 4, would you make K3?
Yes, K3 or 4, 3 or 4, right? Because it is at most. So you can have no empty boxes, which would be that, K equals 4, no empty boxes, or at most one empty box, so K equals 3. Yeah, perfect. So this one is, this answer is S83 if we allow one empty box, but it's also okay to have non-empty boxes, right? So one empty box or no empty boxes.
Okay, yeah, I see that now. I was thinking of it the other way, like you could only go up to 3, but okay.
I see. So that would be
At least or something like that.
at least, yeah. So that would be leaving at least one empty box.
Yeah.
So you can have, yeah. So it's kind of confusing because the K is representing the non-empty boxes, but at most one box is empty. Yeah. So how many non-empty? Yeah, 3 or 4. Yeah.
And so you have to have that. You have to add those two. It wouldn't be either or. It would be both, right? S of 8.3 and S plus S of 8.4.
Yeah, it's plus because any solution here counts. Any solution here also counts. So both of them count. We don't multiply them because we're not combining them in any way, right? So we're just saying any solution here or any solution here. Either one is okay. And maybe what I'll do is I'll say here just as a reference, right? I know that by itself it doesn't say much, but in the table, that would be like the K equals 3 or K equals 4 in that sum.
Okay, thank you.
So I have a question regarding about part B.
Uh-huh.
You have S parentheses 8 comma 4 equals T 8 comma 4 over 4 factorial. I get that part, but then when you go to the equation 1 comma 4 comma 6 comma 4 comma 1, why do you have 5 numbers? Or why is it that you chose that setup? Or
Oh, these numbers. These numbers are the binomials. You see these numbers right here. It's 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. So
okay, makes sense.
yeah.
Oh,
But remember, because it was a small number, instead of writing, here. So 1, 4, 6, 4, 1 is the binomials. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3. And you can compute them. You can compute them all one by one. But remember that this comes from Pascal triangle, right? So 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So that's exactly this.
okay, I need to be familiar with that triangle. Okay.
Uh-huh. So when it's a small number, you can just use your Pascal triangle instead of, because if you try to use the formula for these binomials one by one, it takes a little longer, but this is an easy way to get them out very fast. And so,
Okay, thank you.
Let's see. Part D says, everybody okay up to here?
Yep.
So let's look at the next one. The boxes are identical, so we're still in the Stirling numbers place. No boxes are empty. But then we have this extra condition. B1 and B2 are in the same box. So that's what makes this problem different somehow. So we need to adjust, right? So this is still about Stirling numbers, but B1 and B2 have to go into the same box. So any ideas? Here we need some creativity. Let me remind you about those problems where you have strings and you need to have A followed by, B, A followed by B, for example, in a string. So what you do is you glue A and B, right?
Yeah, I would say treat B1 and B2 as the same ball.
Exactly. Yeah, perfect. So glue B1 and B2. So now how many balls do we have?
7.
7. And it's still same idea, Stirling numbers, right? So, and we still have 4 boxes. So glue B1 and B2. So now the number of balls goes from 8 to 7.
You kind of lost me on that. Wouldn't it, if there are 2 balls, wouldn't we choose 6 over the remaining 3 boxes? Or does it?
Let's see. The boxes are still the same, right? 4 boxes. We're not doing anything with the boxes.
Okay.
But now, imagine that you can put B2 inside B1 or something, because they need to go together. So whenever you pull B1 to put in a box, it brings B2. So it's almost as having a single ball instead of 2 of them. So imagine instead of having balls, you actually have a pair in the back, right? And then you have B3, B4, B5, B6, B7, B8. So those objects together, you can see as 7 objects instead of 8, right? So I have B1 and B2 glued together, and then you have B3, B4, B8. And these are supposed to go into the 4 boxes, right? But these are glued together. They need to, wherever they go, they need to go together.
Okay.
So I have 7 objects instead of 7 objects.
Okay.
4 locations, right?
Yeah, I see it. Thank you.
Yeah. Okay, so let's see the next one. The boxes are identical, so same idea. We're still in the Stirling numbers place. No boxes are empty, and B1 and B2 are in different boxes. So that's what makes it different this time. Before we had the same box, and now we have different boxes. So what do you think we can do?
Can we subtract from the total?
Yeah.
Of the possibility from the part D.
Yeah, perfect. So we count them all, no restrictions, and then we subtract the previous part, which is when they add together. So this is the complement idea that we've used in many places, right? It's a complement. All in B minus the ones in D. Mm-hmm. Okay, so the next one. The boxes are all different. So that changed. In all the previous one, the boxes were identical. So this time around, they're different. Empty boxes allowed. So this perfectly fits into the table, right? Different boxes, different boxes, different balls, empty boxes allowed. Let me just go back very quickly. So that's just this. That's just that. So that would be 4 to the 8, and you just need to remember where the question is where each ball goes. So each ball has 4 possibilities, 4 different balls, 4 different boxes to go into. That's for each of the 8 balls. So 4 to the 8. And just to emphasize, obviously that's easy to compute, but just in case it comes up later, like the different pieces of that 4 to the 8. What if I say, for example, well, actually, let me use this theorem that I added here. Remember this one right here? So I'm just going to write that. I'm just going to expand that summation. That's all I'm doing in the group activity right now, okay? So that summation is as follows. I can either use no empty boxes, that would be the T number, plus, so this is no empty boxes. Or I can have one empty box, right? So if I had one empty box, then that would be T83. But I still need to select which are going to be the boxes that I use. So you know what? Well, yeah, that's okay. So exactly 3 non-empty boxes. So the no empty boxes, and that goes back to Scott's comment from part B, I think it was it? C. It's confusing, the non-empty boxes, how many, or no empty boxes versus how many non-empty boxes, right? So the first one is exactly 4 non-empty boxes, so T84. Not, I don't even know. I'll add it here. So exactly 4 non-empty. or no empty boxes. That would be this, right? And then we have exactly 3. So we need to choose which 3, or we can choose which 2 are non-empty. And so that would be TA2. And we choose which one is going to be used. And that's that. Mm-hmm. So this one is exactly 2 non-empty, and this one is exactly 1 non-empty. Mm-hmm. So let me just ask you something. If I have exactly 1 non-empty box, how many possibilities do I have to do this? So just this last part. I have 4 different boxes, 1 blue, 1 green, 1 red, 1 yellow. Mm-hmm. And I want to distribute 8 balls into exactly one of those boxes. In how many ways can I do that? Forget about the numbers.
Question about F. If it's 4 to the 8 power, wouldn't that still give the possibility that oh wait, never mind. I thought it was no empty boxes are allowed. So never mind. Since it is allowed, then it freely opens the range where like I could choose maybe to put all the balls into the same box, or 2 boxes of the 4, 3 boxes of the 4, or all 4 boxes. Okay, never mind.
Yes. And of course, the easy answer is 4 to the 8, but I want to go a little bit deeper into what it means so that we can solve other problems, right? But let's go back to my question here. What if I have 4 different, forget about the numbers, just try to solve it in a different way. What if I have 2 different boxes, just this? So I have a blue box, a green box, red box, and a yellow box. And I have my 8 balls that are supposed to go into those boxes. But I want to use exactly 1 non-empty. And how many ways can I do that?
Is it just that 4 choose 1 because they'd all be in one of the 4 boxes?
Exactly. 4 choose 1, right? So I just choose which box, and that's it. Everything goes into that. Yeah, that's right. So what is T8-1 equal to?
I'm going to go out on a limb and say 4.
Wait. Almost. I have this 4 choose 1 here. Right? This 4 choose 1 chooses the box that you were saying, right? That's the 4. So what is this?
It's just 1.
Just 1? Yeah. Just 1. Mm-hmm. And this is true in general. So in general, TM1 is equal to 1 always, because this is, the number of ways to place M different balls into 1 box. Just 1. Everything goes into that box, right?
And that corresponds to that binary entry too. It'd be 1 times 1 to the 8th or whatever it is.
Exactly. Yeah. So time is over. Here's the plan. We'll continue with the class with the activity next time. So we'll finish this up. I'll have some more of these examples that are again partial. So these are really parts of the sum that will give you the S84. We don't see them because we have a shortcut for it with the TMN, but those are parts of that. So I'll bring a set of maybe a few problems that are like this, so that you can see other variations, and we'll go over this last part. Okay. If you have questions on any specific wiki problems on Thursday, if you want, bring them, and I'll try to help you out with that so that you have a little bit of help before the due date. And I might, depending on how we're doing, I might move the due date of some of the problems, but just only some of them in section, especially section B maybe, just because it depends on how much we can do, right? So, but I'll let you know. I don't want to move it for all of them because then everybody, we all get behind. So, but I might select a few depending on, how much we did today and how much I believe we can do on Thursday. Okay, guys?
Okay,
So
before
thank you. Yeah.
before I get going, I send you a message on the chat box.
Yeah. Yeah.
I didn't
So
hear
about the exam, here's
anything.
the information about the exam. So I just moved the exam to. Sorry, Elizabeth. It was just, I didn't want to interrupt in the middle of the class, but yeah. So this was the announcement for the exam. The exam is not in a week as it was announced at the beginning of the semester. I just moved it 1 week later, so now it's on the 9th.
Okay.
And the wiki problems, the due date was originally the Thursday, the 25th. So what I'm doing, because now we have a little bit more room, if you want comments, then have them ready by Thursday. Otherwise, Saturday, so everybody can have a final version by Saturday. But if you do it by Thursday, I can give you comments so that you can make corrections and still get full credit between Friday and Saturday.
Tuesday and Thursdays are usually the days that I drop her off, like around this time.
Mhm.
So if anything pops up, I'll go ahead and email you.
Yes, no problem. Just let me know. And remember that I always have the notes on Canvas. So,
Hi, Professor.
bye.
Just in case I never make it to class or something like that, usually because I'm always on the go with her.
Yeah, no problem. Just, if you're late to the class, again, I saw your message, but I didn't want to interrupt.
That's
But that was kind of my next thing to do. But I always will have the notes on Canvas. You can always check them out. And if you see something that that doesn't make sense or that you miss that you want to review, you can always get them out hours or ask me or, we'll find a way.
Yeah, I'm just hoping that she stays strong today and Thursday nothing pops up because her dad passed away on Sunday. So
Oh, I'm sorry.
yeah, so
Yeah.
I'm gonna keep you posted for sure because I might need some time on the wiki problem if I don't get to it by tomorrow or see what happens because everything's up in the air right now.
Okay, just let me know. There's some room on Friday, and again, maybe your problem will be postponed. Who knows? But let me know how everything goes, and then we can adjust. All right.
All right, thank you.
All right. Bye. Anything else?
I just had a real quick thing. I don't need you to respond to anything right now. I just I sent you an email a few days ago. I was just wondering if you wanted me to send you another email because I don't think you saw it.
Yeah, before you go, let me check very quickly if I don't remember an email from you, but maybe I skipped it. So it's not in my season mailbox. Was it through Canvas, maybe?
No, it was just to the email address that was on your syllabus.
The season. So I don't see it. Like I search for it and I don't see it. Noah, could you?
Okay.
Could you
I'll
send?
resend it after class.
Wait, I do have something. Wait. On the 17th. Oh, sorry, Noah. Yes, I do see it. I skip it. I'll respond to you.
Okay.
All right. Let me see. Is it something easy? Oh, I'll reply to you.
Yeah.
Okay. Thank you, Noah. Sorry, I didn't see it. Even now, I had it in front of me, but it was in between others, and
I totally understand.